square root of 36 times 7. Now, one of the big rules with square roots are, if it's a multiplication, you can pull it apart. If it's addition or subtraction, you cannot. So if it's a multiplication, I can pull this apart to equal square root of 36 times square root of 7, which would equal 6 square root of 7. That would be fully simplified. I'm going to state that one more time. If this was square root of 36 plus 7, you couldn't just pull it apart like this. You would actually have to solve the inside before you do anything. I'm going to get rid of that because that's not actually the problem. All right, so we do have to know how to simplify square roots. And that is one of the ways, is just to figure out the biggest one that goes into it. If you would have picked 4, you just would have had to do it a few times. We'll do that later on when we pick an easy one. So I'll show you what happens if you make a mistake. Our next one. What's the square root of 121? 11. That one is square rootable. So I can take the square root of that one. But I do want to bring something up. When you simplify a square root, you can simplify variables to a power. You just have to remember the rules that are over here. And in fact, it leads to just one rule. The square root of x squared equals x. Square root of x to the 4th, x squared. Square root of x to the 6th would equal x to the 3rd. What would square root of 8 equal? X to the 4th. What would square root of 12 equal? X to the 6th. You divide it in half. You cannot have decimals if you want a proper exponent. You can't have decimals. And right now, if I took the square root of 5, I would have a decimal. So what you need to do is you basically have to change this. I got to say x to the 5th doesn't work. But you know what does work? X to the 4th. X to the 4th does work. So we're basically going to pull out an x to the 4th, and it's going to look something like this. So this is the same thing as if I had, I'm going to leave the 121 for now. We know that one works. What I'm going to do is I'm going to write what would work. What's the closest thing to x to the 5th that worked? Well, if I had x to the 4th, that would work. That means I need an x to the 1st outside of this. So I'm going to say, well, if I multiply this by x to the 1st, oh, cool, that will cover my x to the 5th. X to the 4th times x to the 1st would equal x to the 5th. So I'm just pulling that out. I'm saying get rid of it because I can't take the square root of it. Everything else that's in there, you can take the square root of. You can take the square root of 121 and come up with 11. You can take the square root of x to the 4th and get x squared. You can take the square root of x to the 6th and get x cubed. And we're left with that square root of x that we can't do anything with to simplify. And that's it. So if you have variables, you have to knock it down to an even power so you can have it evenly.
How is the square root of the 6th of 3?
Because I'm taking the square root of x squared, x to the 6th. So I said, ooh, I missed the variables, didn't I? That should be a y. Embarrassing. Penmanship ruined me again. That was that y to the 6th.
Well, why does it go to 3? Oh, it's just, oh, okay. No, I didn't see that. Oops.
Yeah, that's okay. That's okay. So when you take the square root of something, you're actually having your exponent. We'll talk more about that when we do powers to powers. But maybe a better way to look at this, and we'll talk about this in a second. We'll put it more.
Exponents are halved in roots?
Yes. So this right here is really x to the 6th to the 1/2. So you can always write a radical as an exponent. So this really is x to the 6th to the 1/2. You have it, and you get x to the x cubed. That's honestly what's happening exponentially wise. Otherwise, you just have to remember what's happening here. So if this was cube root, we'll talk about this in a second, this would be raised to the 1/3 power. And we'll talk about that later. All right. Are we clear on that? All right. Then the next thing is adding or subtracting radicals. Well, in order to add or subtract a radical, you have to understand how you combine things through adding and subtracting. You need like terms to combine things. If I have a red ball and another red ball, I have 2 red balls. If I have a red ball and a blue ball, I have a red ball and a blue ball. I can't say I have 2 red-blue balls. Just like with x's and y's. 2x plus 4x, that's 6x. 2x plus 4y stays 2x plus 4y. So with radicals, right now, if I have negative 5 square root of 32 plus 7 square root of 18, as written, I can't combine them because they're not both the same thing. If they're both square root of 18s, I could combine it. Well, that doesn't mean we can't combine it. What you need to do is you need to simplify first. That's why we started with simplifying. We need to simplify both of those square roots to see if we can combine them later down the road. So we look at negative 5 square root of 32. Now, my job is to recognize that 32 has a perfect square in it. It actually has two perfect squares, but one's bigger than the other. Does anyone see a perfect square that goes into 32? 16 and 4. 16 will be a better one. You want the bigger one of the two. So I'm going to rewrite this as negative 5 times the square root of 16 times the square root of 10, or 2. That's why I strongly encourage, I keep saying, take out your calculator and actually try this stuff. Don't just eyeball this stuff. Try it and see if it works. And then we'll have plus 7. 18, 9 goes into that. 9's a perfect square, so I'm going to turn that into square root of 9 times square root of 2. All right, so we know that square root of 16 is 4. The square root of 9 is 3. So we now have negative 5 times 4, which would give me negative 20 square root of 2, plus 7 times 3, which is 21, square root of 2. Remember, the number in front of something tells you how many you have. So I started with negative 20 square root of 2s. I know that doesn't make sense because you can't have negative something. But you have negative 20 square root of 2s, and I add 21 square root of 2s to your pile. You're going to end up with 1 square root of 2 left, which we should probably just write as square root of 2. So this works just like if I would say negative 20x plus 21x equals 1x. Same philosophy. We're combining like terms. They have the same square root of 2. So I can end up with an actual square root of 2 combining them together. Okay, we got to do the same thing for the next one. The next one's more complicated because there's a lot of elements going on, so you have to take your time writing it. All those people that look for the quickest way to write something, this isn't going to be the problem for you, nor will be the next one.
If they're the same radical, though, and you're multiplying them, they just combine together? They're just the same thing?
Mm. So we're talking about multiplication versus addition, right?
If you're adding them together, my bad. They're just the same thing.
If we're adding them, they're just the same. It's just like if I did negative 20x plus 21x.
They just get pushed into one.
They get pushed into one term because you're telling you how many you have of something. So if you have 3 red balls plus 4 red balls, you better tell me you have 7 red balls. These are your red balls. All right, as long as they're the same thing. Now note, if this was square root of 3, there's nothing I could do because that's a red ball and a blue ball. You'd have to just leave them separate. So if this was a 3, if this turned out to be 21 square root of 3, you're done. You can't push them together.
Why wouldn't it be like root 4, though, when you add them together?
You can't add roots together.
Oh, okay.
All right, you can multiply them, but you can't add them.
Okay.
So for instance, if I did square root of 2 plus square root of 3, like I said, that does not equal square root of 5. That actually just stays the same. And sometimes it's easy for me just to tell you rules, but sometimes you can just check them to make sure they work. So if I picture like square root of 9 plus square root of 4, I know that should equal 3 plus 2, which is 5. But if I made this square root of 13, oh boy, something's wrong. Something's wrong. Yeah. Multiplication, you can multiply them, but you cannot add or subtract them. If I asked you to multiply this, so square root of 2 times square root of 3 would be square root of 6. Multiplication works.
Okay.
All right, for the next thing, I'm going to note that I have 72s. I got some x to the fifths. So the first thing I'm going to do is I'm going to figure out things that I can actually take the square root of. What goes into 72?
9.
That's a perfect square. What was that?
9.
9 might go into it, but 36 would probably be the better one. I'm going to show you what happens if you make a mistake. It just takes a little bit longer. So I'm going to say I can do square root of 36, and I can also do the x to the fourth. So I'm writing everything I can take a square root of. I'm basically factoring out all the stuff I can take the square root of. And then I have to write another square root of all that crap I can't take the square root of. So square root of 36 leaves behind a 2. X to the 4th, I need an x to the 1st here. Because this is all factoring out. It really is factoring out. I'm factoring out a 36. I'm factoring out an x to the 4th. Leaving behind the stuff I can't take the square root of. Does that make sense? You be sure. We're okay with that. Okay. Then I have a negative 3x. This one's a more difficult one. Did anyone find a perfect square that goes into 242? 121 goes into it. Correct. So 121 goes into it. I have x cubed. What can I actually take the square root of? What's the closest thing I can take the square root of? I can take x squared. So I want x squared. We know 121 times 2 would give me that 242. And then I'll have x to the 1st hanging out there. So I'm breaking it apart into things I can actually take the square root of and things I cannot take the square root of. So I can take the square root of 36 and x to the 4th, but I can't take that 2 or that x to the 1st. Now we're going to take our square roots. So this is going to equal 4 times 36. Square root of 36, which would be 6, 4 times 6. X to the 4th squared would be x squared, or square rooted would be x squared. I'm going to leave that square root of 2x. That was the point of having it. Minus 3x times the square root of 121 is 11. The square root of x squared would just be x. So I have times x. And then finally I have the square root of 2x. Now we have to simplify, and I would like us to be able to realize that these have the same square roots, so I am going to be able to add or subtract. Usually if I give you one of these, you're going to be able to add or subtract. So if it comes out that they're not, on a quiz or something like that, maybe raise your hand and say, am I doing this right or wrong? Maybe I can catch a little mistake. All right, let's do the multiplication and stuff. 4 times 6, that is 24. X squared, square root of 2x. We got a couple things happening here. I have a negative 3 times 11, which will give me a negative 33. I also have an x times an x, which will give me x squared. And then I have a square root of 2x. Lots of good things for adding and subtracting. I have x squareds, I got x squareds, I got square root of 2x's. So I really have, how many x squared square root of 2x's do I have? I have 24 of them here, and I have a negative 33 of the same thing over here. As long as you have numbers in front of the exact same thing, you can add or subtract. So once again, as long as it's the same thing, which it is, I can add or subtract. So we're just going to have a negative 9 x squared square root of 2x. Now is the time to ask questions because we're moving on to multiplication. But multiplication is pretty much the exact same thing. Copacetic? All right. Then let's move on. Let's move on to multiplication. Multiplication really is just rearrange things you can actually multiply. You can't multiply a constant by a radical, but you can multiply constants by constants. So what I'm going to do is I'm going to change the order in which this is written. I'm going to change this into 7 times 3 times square root of 3xy squared times square root of 15x cubed y. And the reason I'm doing that is because when you multiply square roots, as long as it's the same symbol, that square root, I can put them all under one big square root. You can multiply square roots. Yes. So this whole thing is going to equal 21 times, and I'll show you what I'm picturing. I'm picturing this all under one big radican, or radical. Oh, did I pick the wrong ones? No, I'm good. I did 7 times 3. So I moved the 3. So I took this 3 here
Oh, I didn't see that.
and moved it there. All right, now we got to realize you can rewrite this. I'm just going to picture what's happening inside here. In my head, I'm putting together the 3, the 15, the x cubed, the y squared, and the y. I'm going to do those multiplications. So we're going to now have 21 square root of, and I'm going 3 times 15. 3 times 15, that's going to give me 45. In the back of my head, I'm like 45, 9 goes into that. All right, and then we'll have x times x cubed, which is x to the 4th. And finally, I'll have y squared times y, which is y cubed. Keep chugging along. These are longer problems than they look at first. But it's just basic rules you have to follow. So when I'm looking at square root of 45, I'm looking at things I can actually take the square root of. I can take the square root of 9. I can take the square root of 4. I can take the square root of x squared. However, what does that leave behind? You already told me that it's 5. 5, and not 1, but y to the 1, right? Yeah, I'm sure you did. No, I'm kidding. I know you did. Or didn't. One of the two.
I did.
All right, there we go. That's better. All right. We know the square root of 9 is 3. 3 times 21 is going to give me 63. Square root of x to the 4th is x squared. Square root of y squared is y to the 1st times 5y. I don't care if you leave the y to the firsts. I like them. They told me what I did. I can follow it backwards. Sometimes it's nice to have those numbers, but this is fully simplified. As much as you'll tell me that looks complex, that is fully simplified. Go.
Yeah, he's right.
Sure. You understand what's happening?
I do.
Let that congeal for a second.
When you went from the 45 to the 9 and the 5, why did you only pick a y with it?
I'm looking at things that I can take the square root of. Are we talking here?
Oh, so you could make y by itself.
I want something I can actually take the square root of. I can't take the square root of y cubed, because that would be 1.5. So I'm going to get the next closest thing to y cubed is y squared that I can take the square root of.
That makes sense.
So I missed it.
Yeah.
Move it for the 3 over.
Here?
Yes.
So it's commutative property.
Okay.
Basically, this is like 7 times something times 3 times something. I can move the 3 and 7. I just put them together, so normally I wouldn't even rewrite it. I'd just be, okay, 7 times 3 is 21.
Wow, okay, that's it.
Yep. But just for your benefit, apparently it wasn't for your benefit, but for your benefit, I was doing what I was thinking, that we move the 7 and the 3. No, you're good. It's been a long day, I'm sure. It's been a long week. I just want to make sure in class you understand what's going on. All right, we should all be able to at least start this one. This is a binomial times a binomial. It uses all the rules we just did. So let's go ahead and do that binomial times a binomial. So remember, to do a binomial times a binomial, I use distributing. I distribute that 5 to that 7 times square root of 2 to get me 35 square root of 2. I take that same 5 and I multiply it by that 1 and I get a plus 5. Now, I'm going to switch colors because I want to note that I'm using a negative square root of 2 now. A negative square root of 2, I'm multiplying it here. That's going to give me a negative 7 square root of 4, or 2.
Where'd you get the 5 from?
5 times 1.
Oh, yeah.
Yep. Because I do it this way. I distribute. I'm going to write this all out as is. So I'd have a negative square root of 7 squared times square root of 2. And then finally, I'll take that negative square root of 2 and multiply it by 1. And I will have a negative square root of 2. There are some people that could have done a ton of this in your head. I'm just going to write it all out. You do what you feel comfortable doing. All right. I will note that I have, before I simplify stuff, I'm kind of picturing things I can put together. I could definitely put those two things together. 35 square root of 2 minus 1 square root of 2 is going to give me 34 square root of 2's. I have plus 5. I'm also going to note what happens when you do square root of 2 times square root of 2. You get square root of 4. And what's the square root of 4? 2. Anytime you multiply a square root by itself, you cancel out the square root. So square root of 3 times square root of 3 is 3. Square root of table times square root of table is table. So you multiply it by yourself, but you can look at it both ways, because I'll see people write this as square root of 4 and then get down to 2. We need to realize that this is just 2. So we have 7 times 2, so we're going to have minus 14, which is going to give me 34 square root of 2 minus 9er. I don't know, square roots are complicated just because they look like they're going to be easy problems, and it's just so many little steps baked into one problem. Lots of places to make dumb mistakes. Clarify to yourself why you're doing stuff. Don't just memorize, oh, I want to make these even. Know why you're making them even, because it's the only way to take the square root of them. The only way to take the square root of something is if it's even powered. All right, those are the big things we need to know about square roots. Let's talk about what happens when I divide square roots. You cannot have a square root in the denominator. I'm going to do 3 cases. These are the 3 big cases of what happens if I have a square root in the denominator. First thing I'm going to look at is we have 6 over 2 times square root of 480 over square root of 6. What I'm looking at is, does 6 go into 480 evenly? If it does, I'm going to choose one method. If it doesn't, I'm going to choose another method.
Yep, 80.
It goes into it 80 times. So this is what I'm going to do. And just bear with me here for a second. I'm going to spew some rules real quick. If I have square root of 3 times square root of 2, that equals square root of 3 times 2. If I have square root of 6 divided by square root of 2, I can rewrite that as a big 6 over 2 all underneath the same radical symbol. That's important because on this case, what I am picturing, I'm going to write this really horribly, but I have 6 over 2 times 480 over 6. I'm going to turn this into one big radical symbol. I'm going to turn it into one big radical symbol because 6 goes into 480. And we do have 2 different fractions. We have 6 over 2 times square root of 480 over 6. Well, 6 over 2 is easy enough. I hope we can do that one. That's 3. 4.75. No, 6 divided by 2 is 3. And we'll have square root of 80. Let's simplify this wrong. Do we agree that 4 goes into 80?
Probably like 12 times.
Can we plug in our calculator if we don't agree with me? If you don't agree with me, plug in your calculator. Does 4 go into 80? Is 4 the biggest square, perfect square that goes into it?
No.
It is not. But let's follow the logic that I made a mistake and I didn't find the biggest one. So I'm going to rewrite this as 3 times square root of 4 times square root of 20. 3 times square root of 4 is going to be 6 square root of 20. Is there a perfect square that goes into 20? Yes. 4 goes into it again. So you'd have to do it again. You'd have to go, oh, I made a mistake, and I need to write this as 6 square root of 4 times square root of 5. That would equal 12 square root of 5. By picking the wrong square root that goes into it, it just adds the length of the process. Versus, what's the biggest square root that goes into 80? 16. Versus, if I would have realized that it would be 3 square root of 16 times square root of 5, 3 times 4 is 12 square root of 5, and I'd be done. So just taking a second and seeing if there's another bigger perfect square that goes into it can save you work, but it doesn't mean you're screwed. If I pick the wrong one, I have to realize that I have to kind of keep plugging away at it. Yeah. Yeah.
No.
Okay. On the next one, does 3 evenly go into 8? No, so I'm not going to use the same method. Instead, I'm going to move that square root to the top by using multiplication. I'm going to say to get rid of a square root in the denominator, multiply by that square root, because that would give me 3. Well, what I do to the bottom, I have to do to the top. This is now going to give me 6 square root of 3 times 8, which would be square root of 24, all over 4 times. What happens if you multiply a square root by the same square root? It gives you that same number out without the square root. In other words, square root of 3 times square root of 3 is square root of 9. Square root of 9 equals 3. So this would be 4 times 3. Let's do a little bit of work. 24, is there a perfect square that goes into 24?
No. 6.
Does 4 go into it? Yeah, 6 isn't going to help me. Has to be yeah, I got you. Words are happening. You were correct. So my top is going to become 6 times square root of 4 times square root of 6, all over 12. 6 times square root of 4, you should get out 12, because square root of 4 is 2. So on top, we'll have 12 square root of 6 divided by 12. 12s cancel out, and we just have square root of 6. So dividing, we have 2 kind of options. One is I turn it to one big fraction because I can simplify it. The other method is multiply the bottom by square root to get rid of that square root. Okay, now what happens if the square root isn't hanging out by itself? Like in number 9. Well, watch what I'm about to do because it's incorrect. Well, first thing, incorrect. That's not true. They're not chained by multiplication. You can't just cross them out. Okay. Second thing I see mistakes done is people multiply the bottom by square root of 5. However, if I multiply by the bottom square root of 5, I do get a 5, but I also get a 4 square root of 5. I just move the square root from one number to the other. It still stays on the bottom. So then you try again. You just keep multiplying by square root of 5 until you fill the whole spot and go, it's impossible, Mr. Pabian. All right.
That's only when you have plus, right?
That's only, or minus.
Yeah, plus or minus.
Yeah.
When you have like
Yeah.
square root of 5, or 4 square root of 5, then you can.
Then you can multiply by the square root. Okay, so we have to pick something else. I have 2 terms. Is there something, this is probably a horrible question. Kind of. We're thinking of something along those lines. We're thinking of, so who said that? What'd you say? Conjugate. We want to create a difference of squares. If you create a difference of squares, you square the first thing, you square the second thing. If you square this, you get rid of the square root. If you square this, you get 16 out. So I get rid of the square roots. So we're going to multiply by the conjugate, but in my mind, I'm just trying to create a difference of squares. So if I have square root of 5 plus 4, what would I need to multiply that by to create a difference of squares? I would have to put a negative in there. So we're going to multiply this by square root of 5 minus 4, but I have to do that to the top 2, square root of 5 minus 4. Honestly, multiplying by the conjugate, the bottom should be easy. The top will be more difficult. The bottom should just turn into our square root of 5 squared minus 4 squared. Guys, shh. On the top, we're going to distribute. So I'm going to take this 3, I'm going to multiply it by the square root of 5. I'm going to take this 3, I'm going to multiply it by this negative 4. So on the top, I'm going to have 3 square root of 5 minus 12. Then I have to take this square root of 5. What happens when I do square root of 5 times square root of 5? I get 5 out. So square root of 5 times square root of 5, I will have a positive 5. And then I'm going to have a square root of 5 times this negative 4, which will give me a negative 4 square root of 5. I am going to notice in the numerator, I do have 2 like terms. Well, I also have 2 constants, but I have a 3 square root of 5 minus 4 square root of 5, which is going to give me a negative 1 square root of 5. I'm also going to have a negative 12 plus a 5, which is going to equal a negative 7. All over. Now on the bottom, I'm going to go ahead and do this over on the other side. Well, that's going to be 5 plus 16, which equals 21. So we are going to have...
Can you do something for me?
Sorry, would it be negative?
It would be a negative 21. There we go.
It'd be negative.
So we should have a minus 16, which would be a negative 11. No 21s in there. Just a negative 11. Thanks for staying with me.
It'd be cool if there would be a 21 because then you could cancel out with the 7.
You could. Well, no.
Or it'd be
You have to turn it into two fractions, which you wouldn't need to do. All right. Guys, this is technically a correct answer. I'm going to give you a more correct answer. A more correct answer would actually be, so I'll put an or in there. A more correct answer would be a positive 7 plus square root of 5 all over 11.
Can't do that negative square root.
I did two important things here. I put the 7 in front of the 5 for penmanship-wise so that square root doesn't accidentally get lost in there. So typically we put the square roots at the end of everything. I also got rid of the negatives by understanding that if everything in a fraction is negative, it turns it to positive. If you don't believe me, follow along with me here. What's negative 1 divided by negative 2?
1 over 2.
It turns into a positive 1/2. Now, let's expand that. If I have a negative 1 minus x over negative 2, that'd be the same thing as negative 1 plus x all over a negative 2. Your negatives cancel out, and you have just a positive. I will accept the negatives one, though. So don't just start making everything positive because you saw this one problem. All right, that is dividing by radicals, the three big cases. Either they go in evenly and you can turn it into it and simplify. You can multiply by your square root, or you might have to multiply by a conjugate. The last thing we're going to talk about is, hey, square roots can be written as exponents. Square roots can be written as exponents. So I put a little recall there. Recall that a to the m over n equals n square root of a to the m. I also picked out two very close problems that are vastly different in answer. Not vastly, but slightly. Okay, so our very first one, we have 5k cubed. Is the 5 being cubed? No. So what I'm going to put here is this one does not equal. It does not equal 5. Let's go. Does not equal 5k to the 3 over 4. That is incorrect. The 5 is not affected by that 3 at all, so it shouldn't be on that exponent at all. Instead, this should equal our quantity. Now watch what I do. I put the k cubed all in a parenthesis, and we raise it to a 1/4 power. So you can either write this one in this way, or you can write this as 5 to the 1/4, k to the 3/4. Because you could, I know it's the wrong term, but it's kind of like you distribute that 1/4 to both of them. You're raising a power to a power. Now compare that to the next one. The next one has the entire quantity being cubed. I'm also going to note that anytime we have a square root, we have a 2 out front. So that 2 is going to be the bottom of our fraction. Whatever your root power is, that's the bottom of your fraction. So this is not finished, but these are steps I'm looking at. So we have 4y cubed raised to the 1/2 power. Oop, I wrote that incorrectly. I'll fix that. We have 4y quantity cubed raised to the 1/2 power. which we could then write as 4y quantity 3 over 2. So the entire thing is getting that 3 over 2. So there's a big difference if there's parentheses. So my advice to you is when you have a bunch of stuff in there, put the entire thing around parentheses and then raise it to the fractional power. Yes?
Why did you put a 2 without?
Why did I put a 2 here? Anytime you do a square root, there's always a 2 there. We just do it so much that we don't write it. It's kind of like, you know how we do 1x? We don't write a 1 all the time. Whenever you take a square root of something, there's always a 2, a hidden 2 there. Anytime we get to a bigger power, we always write it, like 4, 3, 5. So know that every time you wrote a square root, there was always a 2 there. So you know to raise it to the 1/2 power. That's where that term square root comes, like square 2 kind of thing. So if I have like 4 squared, you know you're raising it to 2 power. So square root is you're doing the opposite of squaring something. You're doing the square root. Is that better? Okay. All right. Now we're supposed to write these in the simplest radical form. I don't want to interrupt. We good? Okay. So what I'm going to notice is the bottom of the fraction. That is your radical. That's what you're doing a radical of. So we're going to do it to kind of a 2 radical, which is our regular square root. So that's the power of our radical. So we're going to have a 2 root, which is a square root, and we'll raise it p to the 9. That's not too hard, but it does say that we have to put this in the simplified radical form. Simplified radical form means that whatever I could take a square root of, I do take the square root of. So I'm going to rewrite this as things I can take the square root of. What can I take a square root of that's close to the 9th power? I could take to the 8th power. I'm also going to get rid of this square. I'm just going to write it as this. I'm going to say I can do the square root of p to the 8th. But that means I'm going to leave behind a p to the 1st. Square root of p to the 8th would be p to the 4th. Square root of p. That is fully simplified. What 2? Oh, it's always it's always there. It's kind of like when I write 1x, do you write the 1 all the time? No. So if I write a square root, know that there's always a 2 there. You always leave a 3 or 4. You'll notice when I do 3s and 4s, I will always write them continuously. Did you have a question?
This one until the next question.
Oh, okay. Okay. So before we start the next question, we have to go back to this fact. The square root of p to the 8th is p to the 4th. Do we agree with that now?
Yes.
Are we okay with that? It's because we have it. Well, look at this note I have here. If I'm taking a cube root of something, I am going to divide the exponent by 3. So the cube root of x to the 6th becomes x squared because I divide by 3. If I do, let's put another example there. Let's say I do a 4th root of x to the 12th. Anyone want to take a guess at what the 4th root of x to the 12th would equal?
3.
It would equal 3. It would equal x to the 3rd. I knew what you meant. It would equal x to the 3rd, because if I'm raising to the 4th power, I actually divide my exponent by 4. So if I have 5th root, I'm dividing my exponents by 5. That's going to be important in a second. So right now, in order to put this under one square root, they all have to have the same denominator. So I have a 3, a 3, a 3. That means it's a 3 root problem. So we're going to have a 3 root. I'm going to have 27 to the 1st. I'm going to have r to the 17th. And I'm going to have s to the 8th. Now I got to figure out what I can take cube roots of. Remember, a cube root is I do the same number, multiply, multiply, multiply. 27 should be an easy one. Well, 2 root would be 2 times 2 times 2. 2 2 times 2 is 4, times 2 is 8. Okay, that's not going to work. 3 times 3 times 3, 3 times 3 is 9. 3 times 9 is 27. So I can take the cube root of 27. So let's do what we can take the cube root of. I can take the cube root of 27, so that's going to work. Can I take the cube root of 17? In other words, does 3 go into 17?
No.
No. What's the closest number to 17 that 3 can go into? 15. So I can take a cube root of r to the 15. What's the closest thing to 8? It can't be higher. It's got to be lower. We're going to have s to the 6th. Now let's write what we left behind. I left behind a r squared, and I left behind an s. Looks like I left behind an s squared as well. Notice this is still a cube root. Don't forget about adding that cube root. It needs to be on both of these. Now we're going to take the cube root of the stuff we can take the cube root of. Cube root of 27, I said, was 3. Cube root of r15 is r to the 5th. Cube root of s to the 6th will be s squared. And we still have all that crap I couldn't actually take the cube root of. One more thing we got to do before we get to our homework. If I have exponents and division, we still follow the same rules. We're still going to use that subtraction rule. So when I'm looking at this, I'm going to have m to the 3 over 2 minus a negative 2. When you subtract a negative, it turns into a positive. Subtracting a negative turns into a positive. So that means I actually have m to the 3 over 2 plus. I only can add things that have a common denominator.
4 over 2.
I need to turn it to 4 over 2. You are correct. So I change that to 4 over 2. Suddenly I have m to the 7 over 2, which I can rewrite as, oh, that's a normal square root, m to the 7th. I had to change 2 into 4 over 2 so I can combine the fractions. To combine fractions, you have to have a common denominator. So I changed 2 into 4 over 2 so I can combine them. All right.
You could do that another way.
What was that?
You could do that another way, right?
Maybe. We'll talk about that in a second. Let me finish this real quick. So we know we are doing a square root. I could do a square root of m to the 6th, leaving behind a square root of m to the 1st, which is going to equal m cubed times square root of m. All right. Enrique, you said there's another way. What way would you have done it?
So I would have simplified the m3 over 2 to
Square root of m cubed.
square root of m, to square root of m squared times the square root of m.
I got you. Yes, you could have done that.
And then times,
I got you. You can do that. That's correct. Yes. Okay. So this number tells us what I would divide by.
Okay, so,
I would divide by 2. So if there's nothing you want to do, 2, so everything else will be labeled. 1, 2, 3, 4, 5. If there's nothing. Okay, Hey guys, we got 1 minute left. I don't care. Have a wonderful weekend. Don't come on Monday. I won't be here. Remember, your quiz is next Friday. Your quiz is next Friday. We have one more topic, complex numbers. So that's 35 squared. I have 35 squared cubes, right? Someone takes away one. Oh my gosh.
I thought that was true.
I bet for like after there you would have like immediately. So let's just look over here. So this is right? This is pretty much the 1/3 which means you divide exponent by 2.
Okay, yeah, that's good.
So I'm gonna go 15 divided by 3 will give us
Yeah, I know. I'll pick up right today, Johnson. I'm gonna have to do that.
So if it's 3, you have to make sure these are divisible by 3.
Okay, and that's where, that's where you're changing that. Oh, okay, yeah. That's why you're changing those.
I'm changing those to divisible by 3. So if this was a fourth power, I would need something that's divisible by 4. So that's why I changed it 12. Yes.
Thank you. That makes a lot more sense.
Okay. Yeah, I know. I can't give us enough examples. I have to do a lot of concepts all in one day.